On our planet, we have the perfect energy source to harness the power of the sun. No, it's not solar. It's oil, it's coal, it's natural gas. Fossil fuels are the sun's energy collected and concentrated from ancient plants from millions of years ago. The average rail carload of coal weighs 100 tons. The United States burns 1 to 2 cars like this every second. That's massive. With the continuing trend of unpredictable weather, we'll always need more energy for air conditioning and heating. Where's all that energy going to come from when we're still so reliant on fossil fuels? We simply can't sustain the current growth without creating an imbalance in political, socio-economic, and environmental systems of the world. It's an incredible 1 in 6 deaths globally is linked to air pollution. Whether the imbalance is caused by peak oil, effects of climate change, or a booming world population, our current recipe for energy is unsustainable. The status quo just won't do anymore. There's got to be a better way, not pie-in-the-sky promises of what will come, but what we've got that works today.
Our planet, formed long ago by an explosion of energy, held fast through billions of years by energy, and today dominated by a species that has learned to harvest the power of that energy for survival, for prosperity, for progress. Globalization. Without it, humanity could not maintain its modern way of life. Most everything consumable is grown or manufactured somewhere else, sometimes passed between country to country before it enters our individual orbits. Consider that the average supermarket item travels a staggering 2,500 kilometers before it reaches your kitchen, to say nothing of the countless items that have become indispensable to our lives, manufactured on the other side of the world. If the world's economy continues to grow at 3% a year, then every 24 years, the size of the global economy doubles. By 2030, our population will be 8.6 billion people. And the motor of this astonishing growth, energy. Every single thing that we use in our day-to-day lives is created and maintained by energy.
I realize for lots of people, energy is an emotional issue. For others, it's economic or political. It's difficult to think logically about how to fix it for all of us. I've always tried to present the facts as I say them, even if people don't want to hear them. My career as an engineer spanned 37 years. I worked on big projects, from designing and starting up chemical plants to research and development on such things as new construction materials, pulp and paper processes, and finally, focusing on alternative energies. And that was back in the 1970s. When I retired, I noticed what was happening with humanity and the importance of our energy systems and how they shaped our way of life. And even though our technology has advanced from the simple internal combustion engine, the energy of our technology today still mostly comes from that black, oily stuff in the ground. Everyone wants the latest flat-screen TV. Making that TV requires the energy equivalent of 7 gallons of diesel fuel. That's enough energy to run the average American home for 10 days, or drive the average car for almost 400 kilometers. And that flat-screen TV is now a smart TV, so it's connected to the internet like many other gadgets these days. The internet is really just a collection of power-hungry data servers. Some US researchers predict that these data servers could use 3 to 20% of the world's electricity by 2025. By 2020, other estimates indicate that information and communications could consume more energy than aviation and shipping combined. Then, you get in your car and drive 3 miles to the big box store to buy that TV using gasoline in a car that has 7 gallons of oil in each tire and was built using large amounts of energy, most likely from coal, oil, and natural gas. The TV is in a box made of wood pulp, harvested and manufactured with energy. It's then wrapped in plastic and styrofoam made from oil. On and on it goes. We owe so much to energy, and specifically to fossil fuels, that we simply couldn't exist as we do now without them.
It's always available when we need it, to power our lives, our homes, our businesses, our cities and countries, seemingly at the flick of a switch. We see the electrical lines, the power stations, but how does it all work?
Electricity is really generated one way, by using mechanical energy to turn a turbine to create electrical energy. And how that turbine turns is a function of heat. We have to burn some sort of fuel to create steam, or use the force of water to turn it. The way we produce large-scale electricity hasn't changed in over 100 years.
Here was a light that was to show the way to one of the most significant single developments the world had ever seen. The electrification of nearly all human endeavor. No longer would light, heat, and power have to originate at the points where they were to be used. They could be delivered by wire from central power stations. Now there were companies manufacturing something that no one had ever made and sold before. They were manufacturing the most versatile power of all time, electric power, and delivering it through wires no bigger than your fingers.
To get to us, electricity needs to travel. It goes through miles of high-tension lines from the generating station to reach us. And when it is received at substations, like the ones you see in your city or town, it is stepped down so it can be distributed to consumers. This system is called the grid. The grid does not store electricity. It is always in a state of dynamic balance. Electricity is used on demand. Storage of a large amount of electricity is difficult and not very well developed. If electricity is generated and not used, it is lost. But yes, we all know electricity can be stored in batteries, but can it be stored at the volumes we need?
To create a backup system to store enough electricity to run your house for a week would require a battery array weighing 2,300 pounds. And the cost of the battery over its life cycle would triple your electricity bill. At grid scale, battery backup systems to store massive amounts of unused electricity is, today, simply impossible. There are bold predictions that battery technology is the future for energy storage. But even the latest batteries, pound for pound, can only hold a tiny fraction of the energy in gasoline. The equivalent energy in 1 gallon of gasoline would require a battery weighing 430 pounds. For power companies, it's easier to burn cheap, plentiful fossil fuels than to invest in costly, bulky battery systems.
And the strain on the grid is only growing. In 2017, the world needed the energy equivalent to that contained in the fuel tanks of 310 billion cars. In 80 years, it's predicted we'll need the energy in the fuel tanks of 900 billion cars.
As a global community, we know we need to drastically scale back our use of fossil fuels. But how? Renewables are often touted as planet savers, and yet, year over year, they still only contribute a fraction of the energy we need and will need in the future. In 2018, just 13% of the world's energy was produced by renewables. And of that, 9% was from hydroelectricity. Wind, solar, and geothermal contributed only 4% to global energy production. With the constant bombardment of media stories about our changing environment, loss of habitat for animal species, and dire predictions about the future of our climate and way of life, people have taken notice and changed their behavior. But a recent study suggests this movement towards energy conservation falls short when we don't curtail other conveniences of modern life.
Many people try to be conscientious consumers, to buy organic, to recycle, to use energy-efficient appliances. These people's trips to Europe and elsewhere use far more energy than they conserve. It negates any benefits of conservation.
According to Oxfam, the richest 1% produce about 175 times as much carbon as the lowest 10% of the world's population. Wealth requires energy to sustain wealth and power.
Governments are rushing to enact policies to cut carbon emissions to meet the Paris Accord. The UK wants to ban all petrol and diesel vehicles by 2040. Where will the electricity come from to power these vehicles? Right now, it's from coal, oil, and natural gas.
World energy usage has more than doubled in the past 35 years. And with climate change, even more energy will be required in the future. The United States government and military have identified climate change as a high-risk factor in political and social instability. Droughts, storms, and other climate events can not only affect food production, but energy production as well, causing mass migration from rural areas to cities, exacerbating political instability, which can result in war and social unrest. Not only will the world need more energy to effectively deal with changing climatic conditions, but for the production of food.
Food production is extremely energy intensive. We need lots of fertilizers to grow food. Nitrogen fertilizers are usually limited, and they're derived from, you guessed it, fossil fuels. And the many machines required, from seeding to harvesting, are all diesel fuel powered. In developing countries where food production is not as modernized, the strain on energy will be even more pronounced as populations continue to grow.
Incredibly, 1.2 billion people around the world do not have access to electricity. That's almost 1 in 6 people. China and India together account for 1/3 of the world's population. And as incomes rise in these countries, so does the demand for energy. To reach energy parity with the rest of the modern world, China and India may require 4 times their current usage by the year 2100. With the world's 6th largest economy and 4th largest proven coal reserves, the use of fossil fuels to power India's progress is already acutely felt in major cities such as Mumbai and Delhi, which suffocate under a thick fog of air pollution. In a country known for having the worst air quality in the world, by 2040, OPEC predicts a 150% increase in demand for oil.
Which brings me to peak oil. We've heard about peak oil for decades. You don't hear about it in the media much these days, not as much as during the 1970s oil crisis.
In 1973, oil-producing Arab countries implemented an embargo to protest U.S.-Israeli policies. The price of oil quadrupled, but despite the problems it caused for the United States, energy policy did not change. In France, a country that used oil for most of its energy, the reaction was markedly different. They embraced other forms of electrical generation to break their reliance on fossil fuels.
Since 1984, we've been using oil faster than we can find and develop it. In 1940, it took the energy of 1 barrel of oil to find 100 barrels of oil. Today, the ratio is about 1 barrel of oil to find 10 barrels. In the oil sands, because of the recovery process, it's about 1 to 5. This ratio will only get worse as demand grows and sources are further depleted. The world is on the edge of an energy abyss. There are many big ideas to make our energy cleaner and more abundant, but there's very little substance. Look, the US was founded and built on renewable energy. It was built on firewood. The colonies had vast forests for heating, cooking, steam engines, but then the age of oil changed all that. Wood was abandoned in favor of coal because wood didn't have the supply or the energy density to meet the demand of a growing country. And the same holds true for renewables today. They still only contribute a fraction of the planet's energy needs, and that isn't going to change.
We know that wind and solar energy is intermittent. The wind doesn't always blow, and the sun doesn't always shine. And at grid scale, energy generated must be used. There are no backup battery systems. When there is no energy generated by wind and solar, at night or on a calm day, the grid requires backup generation to meet the demand. And typically, that backup is generated from fossil fuels.
To power the US with solar energy requires up to 500,000 square kilometers of land suitable for solar panels. Wind energy has real problems. You would have to cover the entire western half of the US with turbines. Both options are weak and need robust support systems for where the wind stops blowing or a cloud blows over. And the materials alone, steel and concrete for wind electricity factories, far exceed any other energy source. Hydroelectricity is nearly the perfect renewable, always flowing. But again, you need the right geography to build dams, and most of those sites are already developed. Which leaves the last major contributor to world energy, the forgotten fuel, nuclear energy.
Information about the beneficial uses of atomic energy knows no national boundaries. The facts are available today, for nuclear energy isn't waiting to help people everywhere in some brave new world of the future. The peaceful atom is here now to serve the needs rather than the fears of mankind.
In the summer of 2017, the massive tropical storm, Hurricane Harvey, slammed into the Gulf of Mexico, causing immense havoc. unprecedented flooding from the storm shut down 1/5 of the United States' gasoline production. Wind and solar farms were unable to operate. The Arkema chemical plant in Houston erupted in explosions. The price of natural gas and petrol at the pumps surged to a 2-year high. But as traditional power generating plants and renewables such as wind and solar were interrupted, nuclear power was still generating electricity. The South Texas Project nuclear power plant ran at full capacity despite wind gusts of up to 130 miles per hour. From unstable weather in the tropics to the frigid winds of the north, in 2014, 2017, and again in 2019, North America experienced the phenomenon known as the polar vortex, smashing record lows across Canada and much of the continental United States. Electrical grids suffered outages, coal stacks and diesel generators froze, gas lines choked up. The demand for power to heat could not be met. But again, nuclear power stepped in.
The reason is simple. Nuclear reactors are by far the safest and most robust way of producing large amounts of electricity. They can operate in the most extreme weather conditions. During Hurricane Harvey, a Texas nuclear plant kept running the entire time. It has 4 to 7 foot thick reinforced concrete walls, and they can withstand a hurricane, a tornado, even an impact by an airplane. The whole facility is watertight. No other electricity source kept running during Harvey. No wind, solar, coal, or natural gas. Just that nuclear plant. In extremely cold weather, like we see with the polar vortex, nuclear power plants actually increase their efficiency because of the difference in temperature between the inside and the outside.
The robustness and reliability of nuclear reactors should assuage our fears that they are affected by extreme climatic conditions. With a few high-profile accidents over the past few decades, nuclear energy has been a hot potato, both socially and politically. But to understand the place of nuclear power today, it's worth taking a second factual look into this energy-generating source.
Many people are afraid of the term nuclear. I know it's hard to do, but the first step in taking a logical look is to separate the notion of weapon from the term nuclear. Yes, nuclear weapons are terrifying, but that's just one side of a very complex coin.
Prior to the 1960s, the nuclear age and America's integral role in its development was a point of pride. The nuclear bombs dropped on Japan were determined to be necessary in ending the war. Bomb shelters and nuclear attack drills were part and parcel of the Cold War era. The utility of nuclear energy development was another industry that America could get behind. But all that changed in the 1960s and 70s when environmental groups started equating nuclear weapons with nuclear energy, and that nuclear plants were going to release radioactivity that would poison the population. But it was a 1979 Hollywood movie, The China Syndrome, about a hypothetical nuclear plant meltdown that was to energize the anti-nuclear side, championed by the producer and star of the film, activist Jane Fonda.
And so there's an extraordinary moment in the middle of the film when it sort of breaks out of a normal feature film into something approaching a documentary where she shows ordinary mothers becoming politically active to stop a nuclear power plant. Well, here's the plot twist. Just 12 days after China Syndrome comes out in the theaters, there really is a nuclear power plant meltdown.
Near Harrisburg, Pennsylvania, an accident at a nuclear power plant. A spokesman said that a feed water pump broke down this morning, automatically shutting down the 3-mile nuclear power plant. Some radiated steam escaped into the atmosphere before the plant could be sealed off, but officials said there is no threat to health. The plant is 10 miles southeast of Harrisburg.
The movie had an immediate effect on how the media covered the accident. According to the screenwriter of the film, the editor of the New York Daily News asked his reporters if they had seen the China Syndrome, and the ones that responded in the affirmative were sent to cover 3 Mile Island. And while the event at the Pennsylvania reactor resulted in no harmful levels of radiation released, many drew parallels between nuclear energy and the destructiveness of nuclear weapons. Public outcry and political pressure hit the American nuclear industry hard. Plans for expansion were stopped cold. As a result, instead of building new nuclear plants towards a cleaner energy future, the United States continued to build power plants that burned fossil fuels.
So what's the other side? Basically, nuclear power is a fancy way of heating water by splitting uranium atoms to turn a turbine to create electricity. And uranium is so incredibly energy dense. Only 1 kilogram of the stuff could light a 100-watt light bulb continuously for 25,000 years. Uranium the size of a pool ball contains the energy equivalent of 2.3 million liters of gasoline. That's astounding.
Nuclear energy currently makes up about 11% of the world's total energy output. But in some countries, such as France, as much as 75% of that country's electricity is produced by nuclear energy.
So what scares people the most? The answer I get most often is radiation.
Fear of radiation was a rallying theme that came out of the 1960s anti-nuclear movements and had the most traction with the public at large. But it wasn't just the anti-nuclear side that successfully spread the fear. It was also compounded by an inadvertent error made by the governing bodies that regulated nuclear energy. Introduced after World War II in the wake of Hiroshima and Nagasaki, the linear no-threshold dose hypothesis, or LNT for short, was the gold standard in estimating the cancer risk from ionizing radiation. The premise was simple. Increase the dose of radiation, increase the risk of cancers and death. Double the dose, double the cancer. Nuclear and government regulators the world over use the LNT system to shape policy on developing and operating nuclear facilities, and to estimate potential deaths from accidents.
Exposure of the whole body in a short time to 600 or more roentgens of radiation will almost certainly be fatal.
But there's a problem with LNT. The effects of radiation are not linear, and there's no threshold. It does not take into account dose levels or rates, or that our immune systems are effective at repairing cell damage from the normal radiation doses to which we are exposed daily. The LNT model was adopted by the UN during the height of the Cold War and was used to scare countries out of testing nuclear bombs in the atmosphere. The LNT assumes all radiation causes cancer, and it doesn't work that way.
To give an example of LNT logic, we can use over-the-counter pain medication dosage as an analogy for radiation exposure. If you were to take 1,000 Tylenol tablets all at once, it would most certainly kill you. But LNT also assumes you would perish after taking 1,000 Tylenol tablets, one a day, for 1,000 days. As well, if on a particular day 1,000 people each took 1 Tylenol tablet, then one of those 1,000 would perish. Few experts and organizations consider LNT to be valid. With both the UN and the World Health Organization, viewing the method as overly conservative in predicting the health effects from low levels of radiation. The LNT method cannot account for the fact that if you took a sample of 100 people, roughly 40 of those would naturally develop cancer over their lifespans, whether or not they are exposed to radiation beyond the recommended levels. In other words, cancer occurs with or without radiation exposure.
Radiation is everywhere, in everything on our planet. A normal dose is 6.2 millisieverts a year for the average person. It occurs naturally in bananas, in sunlight, and you're exposed to higher levels on a plane. It's in people, rocks, trees, you name it. At low levels of radiation, doubling the dose has no effect at all. It doesn't double the cancers that LNT would predict. If it did, the millions of nuclear workers who've been exposed up to 10 times the average dose would have a higher cancer mortality rate. But they don't. And these workers have been monitored closely for over 50 years since the beginning of nuclear power.
People living in Wyoming and New Mexico, due to the altitude, have twice the annual radiation dose as those living in Los Angeles, but in fact have lower cancer rates. This could not occur if LNT were true, because the LNT methodology renders this premise an impossibility. The people of Ramsar, Iran, live with natural radiation levels over 100 times higher than the world average. And yet, they are as healthy as people living in low-level radiation zones. Naturally high radiation is also found in southwestern France, parts of Brazil, Africa, Switzerland, China, Italy, and many other places around the world.
The LNT system has been used to calculate potential deaths from Chernobyl and Fukushima, and that has fueled the hype that nuclear energy is bad. It's simply not the case. Chernobyl is a good example.
LNT was used to incorrectly estimate the public health effects after the Chernobyl accident. Hundreds of thousands of people were evacuated in a large swath around Chernobyl. Unnecessarily, some experts would argue. Many thousands did die, not from radiation, but from the psychological effects of the evacuation, which led to depression and increased alcoholism. In 2005, almost 20 years after the accident, the International Atomic Energy Agency released a report that stated that the mortality rates of those affected are quite low, affecting mostly the first responders immediately following the accident, contrary to some predictions that estimated hundreds of thousands will suffer ill effects. A follow-up report in 2012 from the United Nations Scientific Committee on the Effects of Atomic Radiation, 26 years after the accident, went further to dispel the radiation hype.
Although those exposed as children and the emergency and recovery workers are at increased risk of radiation-induced effects, the vast majority of the population need not live in fear of serious health consequences due to the radiation from the Chernobyl accident. For the most part, they were exposed to radiation levels comparable to or a few times higher than annual levels of natural background, and future exposures continue to slowly diminish as the radionuclides decay.
Some countries, including Canada, Germany, and the United Kingdom, have conducted studies into the effects of living in close proximity to nuclear reactors. Incidents of cancer in these cases have been shown to be statistically insignificant, meaning that other variables could influence the development of cancer, including carcinogens and natural predisposition.
Over the years, the levels of detectable radiation at most operating plants has gone down, well within safe limits, to fractions of a percent. When designed right, run right, the nuclear industry is among the safest in the world. But it's worth taking a second look at the big three: 3 Mile Island, Chernobyl, and Fukushima, the accidents everyone's heard of. The accident at 3 Mile Island, as oddly as it sounds, was a technical success. The reactor shut down exactly as it was designed to. A nuclear meltdown does not result in a release of radiation, just like your car engine overheating doesn't spill gasoline. 3 Mile Island released less radiation than people would have been exposed to living in Manhattan or Denver. Chernobyl was a combination of human error and a specific reactor design. It was used to make plutonium for weapons. Graphite was used in the reactor, which caught fire, causing a sudden, explosive release of large amounts of radiation into the atmosphere over a short time. The fact is, due to training in reactor design, an accident like this simply couldn't happen again. Fukushima, on the other hand, was brought about by a natural disaster, and the resulting damage to cooling systems led to a comparatively slow release of radioactive material over several days. The reactor at Fukushima was 40 years old, of an older design, and hindsight suggests that if the fuel tanks for the emergency generators had been moved to higher ground, or increasing the height of the tsunami wall, this could have averted the accident. But the important point to note is that the LNT was the methodology used to evacuate 154,000 people from the vicinity of the plant, some would argue unnecessarily. That has resulted in the highest death rates, the suicides, depression, and other factors that result when displacing a large group of people from their homes.
The accident at Fukushima was not caused by complacency. The plant was shutting down as designed until an hour later when the tsunami washed away the fuel tanks for the backup diesel generators. The tsunami wall was 6.5 meters high, but the tsunami that washed in was 14 meters. A similar plant, 110 kilometers north, shut itself down safely in 10 hours. It was at a higher elevation than at Fukushima, and the emergency generators were not affected.
These statistics are from scientific reports into these events. Even if they were, for some reason, incorrect in their assumptions by 50% or 100%, they simply do not compare to the havoc caused by our traditional energy source, fossil fuels.
There is controversy over the amount of deaths caused by particulate pollution from burning fossil fuels, particularly coal. An internet search of the issue will result in all sorts of grisly stats. But one statistic which is factually based is the human cost of mining coal. And in the United States alone, since the turn of the 20th century, an estimated 100,000 coal miners have perished. This alone rates coal, by volume, as one of the more deadlier forms of energy.
The byproduct of nuclear energy is the waste. But if this waste is contained and stored properly, it poses no risk. Unlike the radioactivity in coal, which is burned and sent out through the smokestacks into the environment. If the nuclear regulatory body of your country controlled coal electrical generation, they would shut down every single plant immediately because of the radiation. What is emitted by nuclear plants is steam, so clean in most cases you could condense and drink it.
In the United States, 20% of power comes from nuclear, producing only 2,000 tons of waste a year, the amount of which would not even fill a 3,000 square foot house. Coal, on the other hand, generates over 2,000 tons of hazardous waste every 5 minutes, 400 million tons of waste annually, and in that same year, some 25,000 tons of radioactive waste due to the uranium and thorium released when burning coal. And as of today, an additional 1,400 coal electrical plants are being planned or built worldwide. In comparison, after 5 decades of nuclear power in the United States, all that waste would fit in a single landfill.
The big reveal here is that statistics show that it's not nuclear plant accidents that are the leading cause of death with nuclear power. It's the aftermath, the effects of evacuating people away from their homes and livelihoods. But when you sandwich the numbers together, it's still significantly lower than for all other fuel sources. The deaths from coal alone since 1900 are massive compared to nuclear, but they're largely invisible from pollution. But it only takes one nuclear accident to reach catastrophic proportions in the media that we've become frightened by nuclear energy. But the numbers just don't add up.
Hydropower is by far, at least in the public's imagination, one of the safest ways to generate electricity. But recent studies suggest that the environmental cost of large-scale hydropower have been disastrous. In 1975, about 30 dams failed in short order in central China due to severe flooding, and the people that died in the aftermath were estimated in the hundreds of thousands. From this single event, fatalities from hydro energy far exceeds the number of deaths from all other energy sources.
Nuclear energy is not perfect, but nothing is perfect in the hands of human operators. From cars to planes, accidents happen, and engineers like me learn and build in fail-safes so it doesn't happen again. That's partly the reason why nuclear power plants can be so expensive and take so long to build. The amount of safety regulations is impressive. But in terms of kilowatt hour to kilowatt hour, nuclear is the safest, cleanest energy source, even despite the accidents at Chernobyl and Fukushima. In fact, a group of NASA scientists went even further.
Nuclear power prevented an average of over 1.8 million net deaths worldwide between 1971 and 2009. This amounts to at least hundreds and more likely thousands of times more deaths than it caused.
It literally flies in the face of convention to think that millions have been saved by nuclear energy. But I certainly don't doubt it. The numbers here certainly add up. The evidence is there, and yet there's still pushback. Why? One reason, the hype surrounding renewables. There are still those who say we can move entirely to renewable energies in the near future. We can save the world with wind and solar and tidal energy. While there has been some progress, the long-shot deliverance we are promised is just not happening. And nothing yet has come close to the usefulness of nuclear energy. It's intermittent, needs a support system, because electricity can't be easily stored, requires a large land footprint. They're heavily subsidized and are much more expensive per kilowatt hour than nuclear. Wind and solar make up less than 5% of world energy production. They're really only an energy of politics, not technology improvements. Great idea, using the planet's heat to spin turbines to create energy. But it's only a great idea if you live in Iceland and maybe a few other places where the earth vents heat to the surface. Fuel from plants, what could be better? But on a large scale, growing corn to make fuel has serious flaws. By the time you've harvested the corn and processed it into ethanol, you've used up almost as much fuel as it gives you. And it competes with the food supply, driving up prices for everyone. A lost cause. Future demand outweighs any serious savings we can make. Conservation extends fossil fuel reserves, but the amount is insignificant. Besides, look how things are manufactured globally, how they are transported by freighter using the most polluting fuel. All that fuel burned to transport energy-saving LED bulbs made in Asia. Lighting accounts for less than 4% of household electricity. If all your bulbs are replaced, it would still be negligible to energy efficiency. In winter, you need more heating to make up for the cooler bulbs. TVs, computers, appliances are way more efficient than their predecessors. But factor in that there are millions more of them and that they're increasingly connected to the internet, which means power-hungry data servers again. What this all means is that we're using more and more energy. Renewables such as wind and solar are hardly making a dent in world production. Batteries, as we've seen, are good for small applications, but nowhere near grid scale, and we're still burning a hell of a lot of coal. Even more so, as in the wake of Fukushima, some countries are stalling nuclear power projects or decommissioning others. Germany is abolishing nuclear energy very quickly, but they still buy a ton of electricity from France, which is 75% generated by nuclear energy. And their energy bills are double those of their French neighbors. France has some of the cleanest air in Europe. So what's the stopgap when you ditch nuclear? Coal.
Both China and India get much of their energy from burning coal. But as these engines of industry rev up their economies and bring newfound wealth and living standards to their populations, it comes at a horrible price. In China, a recent study suggests that air pollution may cause genetic harm in children. In India and other developing nations such as Kenya and Nepal, 2.4 billion people still rely on traditional energy sources for cooking and fuel. Dried animal dung and wood, when burned, causes choking particulate smoke to be released in massive quantities. The health effects are pernicious. Globally, after India, China is a close second for early deaths due to pollution. But it's not just a problem in developing countries. A recent US study suggests that for the last 25 years, air pollution from Asia has migrated over the Pacific, increasing smog levels in the western United States, despite a 50% reduction in US emissions of smog-forming pollutants.
It really needs to be a global effort to cut pollution, to cut our reliance on fossil fuels in producing energy. We really do live in a fishbowl, and what happens on one side of the planet affects all of us. So if nuclear energy really is a viable solution to cutting pollution, where do we stand now?
Most of the reactors in the United States are from the 1970s, known as Generation 2 reactors, the same type as found at Chernobyl and Fukushima. While useful and essential to the world's energy grid, these reactors, by today's standards, are very inefficient in harvesting the true potential of uranium. Most reactors found around the world today just burn uranium, known colloquially as burners, the industry standard that went out and was deployed throughout the world. But their thermal design is very inefficient, leaving 99.3% of the energy left in the uranium fuel.
I certainly don't think anyone today would want to drive a 1960s car or type on a 1960s typewriter when you can have a computer or a car with the latest bells and whistles. What I'm saying is, we need to step up to the next generation of nuclear power, more efficient, safer, with less waste. The fast breeder reactor.
The competing design, the fast breeder reactor, makes fuel and is 100 times more efficient than today's widely used thermal reactors. Not only that, fast breeders can use old nuclear waste as fuel, and they are the only off-the-shelf next-generation reactor that we can build now. There is already enough uranium mined to power the world for 2 to 3 centuries. And while the West is slow to change to the next generation of nuclear power plants, there is change happening farther afield. India is the most populous country on the planet, a country of both extreme wealth and poverty. Approximately 270 million of India's 1.2 billion people do not have access to electricity. On the world stage, India is emerging as an economic powerhouse at a cost. The almost Herculean challenge to extend its grid to the poor rural areas would mean a 3-fold increase in emissions from fossil fuels by 2030, not only affecting India, but the entire planet. And while current-day leaders in India say they cannot abandon coal in their quest for an energy revolution, there is a movement to embrace new ideas and a fervor to push the country towards a cleaner energy reality.
While the United States derives 1/3 of its energy from coal, for China and India, it's their primary source. Coal is the largest contributor of pollution in the world today, and the death rates from coal in China and India are significant.
In 2012, India was plunged into darkness with a near nationwide blackout, the worst outage in global history. India's electrical grid is buckling under the strain of climate change and an ever-increasing population.
The biggest challenge today is to provide energy for the humanity, particularly for the developing countries where there's a large-scale growth potential, and at the same time, maintain the balance in the environment and mitigate any possibility of climate change.
The fast breeder reactor is the most promising currently available reactor design. It's been largely experimental in the West, even though it's been around since the 1960s. Countries like the United States, United Kingdom, France, and Germany have built prototype reactors, but they've all since been decommissioned, largely due to politics. But it's in Russia and Asia where the fast breeder reactors still hold great promise.
The Kalpakkam 500-megawatt fast breeder reactor in southern India is scheduled to go online in 2019. Unlike conventional thermal nuclear reactors, which use less than 1% of the energy of uranium, fast breeder reactors utilize virtually all of it.
The benefits of fast breeder reactors are really next level when compared to the traditional thermal reactor. They're 100 times more fuel efficient. The radioactive waste produced by fast breeders has a shelf life of 500 years or less, rather than thousands of years, which is the case with thermal reactors. And the uranium fuel used by fast breeders is not weapons grade, so you can't make bombs. What's more is that fast breeders can use the old waste from thermal nuclear plants as fuel, which is remarkable.
You can see that the spent fuel which is coming out of the reactor is not a waste. It is actually potential for further energy. It's a huge potential. So India has adopted the closed fuel cycle, which is shown in the bottom, and that advantage of getting the fertile to fissile is something which we are exploiting. Our fast reactor is ready for operation in Kalpakkam.
After Fukushima, there was a backlash against nuclear energy. Some countries rushed to shelve sites under construction and decommission others But China and India, which both have a vested interest in developing the next generation of nuclear plants, did something remarkably different.
They are using more advanced technology than what was in Japan. They're using something called passive safety. So remember what I said, the reactor core has to be kept cool. So what they do is they put a whole bunch of containers of water right above the core of the reactor, and by gravity, the valves will open and dump water on top of the reactor. No need to have electromechanical pumps or anything to do with electricity. So that's a very good technique. It's a very advanced design.
China and India are investing heavily in nuclear power. But what's happening here at home?
Besides the political pushback on nuclear energy in the West, building a nuclear plant from scratch remains an expensive, long-term endeavor. It can take between 10 to 20 years to plan and build a functioning plant. Regulatory bodies that oversee nuclear plants have some of the most stringent regulations for any project of this scale.
To build a nuclear plant is sometimes prohibitively expensive due to regulations. But can these regulations be improved and streamlined? Yes. The regulations for the current thermal reactors and fast breeder reactors can both be improved.
Some critics of the Nuclear Regulatory Commission, the governmental body that oversees nuclear power in the United States, suggest that there should be a more common-sense approach to building nuclear plants. Some safety regulations deal with unlikely scenarios, which nevertheless push the price tag of nuclear up, pricing nuclear out of the energy market.
Safety is important, I get that. But increasing the costs for the industry because of these regulations does not necessarily mean increasing security. Nuclear is already one of the safest in the industry, and too many rules means too many costs, and the consumer pays for that. The health of the planet pays for it.
In the past 10 years, people have started to take notice of what nuclear offers compared to traditional modes of generating electricity, and they have been fighting back.
I think people are starting to realize that nuclear is actually safe, and it's really good for the environment. And while governments have been rushing prematurely to shut down nuclear plants in their jurisdictions, as we've seen in California, Germany, and Japan, there have been some victories. Pro-nuclear advocates have saved plants from closing in Illinois, Switzerland, and Sweden. The fact is, the more nuclear plants you close, the more clean energy production declines as more fossil fuels come online. That's happening right now, and it's frightening.
With more electric cars on the road, we may be just trading one fossil fuel, oil, for another, coal, as the burden for charging these electric cars falls on an electrical grid which is already heavily reliant on fossil fuels. But innovative minds in the nuclear industry are starting to offer new ways to bridge the gap for more electrical energy. Reactors that utilize thorium, molten salt, and pebble reactors to smaller, more powerful, safer reactors. These new designs on the horizon show immense promise, as well as an invigorated talent pool in which to hopefully execute them one day.
But while these new designs are exciting, they're still very much in prototype phase and could take many years to develop, which is why I think the fast breeder reactor is the best bet now, not 10 or 20 or 30 years down the road. There are fast breeder reactors in Russia, France, and elsewhere, and they work. India is leading the way in showing that on a commercial scale, fast breeder reactors are absolutely viable. But if the politics of fear continues to influence decision makers, I can't help but see more fossil fuels, not less, being brought online. Compound that with the real risk of twice as many nuclear plants closing than opening by 2030.
You know, sustainability is a word which is too often used without really knowing the meaning of it. When you look at sustainability, sustainability is not in one parameter. Sustainability is human life on this planet, if you look at that way. So sustainability would require everything. You require water, you require food, you require peace. And of course, sustainability also will require energy. Because from the start of the Industrial Revolution, the energy requirement for humanity is continuously increasing.
More energy will be needed to combat the future of climate change and its associated issues, such as famine, mass migration, flooding, and a myriad of other unforeseen problems.
And in North America, we've seen that climate change can also mean an increase in the polar vortex affecting coal and fossil fuel energy generation. When it's as cold as the Arctic outside your door and the grid is buckling under the strain, where is the energy going to come from to heat your house?
Conversely, the summers of 2018 and 2019 saw record-setting heat waves the world over. Each year, the United States consumes more energy for air conditioning than does the entire African continent for their day-to-day energy needs. As the environmental stakes get even higher, nuclear power has also seen some unlikely advocates in recent years. Once unthinkable, it is no longer taboo to be both an environmentalist and pro-nuclear. Environmentalist and author Stuart Brand of the Whole Earth Catalog and Sir Bob Geldof, artist and political activist, are staunchly pro-nuclear power. The New Guard, born in the era of accelerating climate change, include Mothers for Nuclear, Eric Meyer of Generation Atomic.
As an environmentalist and a person who's worried about climate change, it makes me sad and makes me worried about the future. So I think if we can come to Germany and if we can change the Germans' minds about nuclear power, we can change everybody's minds about nuclear power.
An environmentalist and California candidate for governor, Michael Schellenberger. Richard Branson, Bill Gates, Jimmy Carter are just some of the more high-profile supporters of nuclear energy, joining a growing list of scientists, politicians, business leaders, and people from all walks of life that are beginning to understand the potential of this limitless energy source.
I think it's natural that those of us that became very concerned about climate change, such a big environmental issue, would gravitate towards really romantic solutions like harmonizing human civilization with the natural world using renewable energies. But I think it's also understandable that as the facts have come in, that many of us have started to question our prior beliefs and change our minds. For me, the question now is, now that we know that renewables can't save the planet, are we going to keep letting them destroy it?
For some countries, such as Japan, Korea, and Taiwan, nuclear power is cheaper than natural gas, cheaper than petroleum, and sometimes even coal. But for other countries, the fear of nuclear continues to seriously curtail the industry, if not shutting it down altogether.
Nuclear power is a topic that stirs a lot of passion, and it's become more than simple economics and politics for the nuclear side. People do care about what the pursuit of energy is doing to our planet, and I do hope, for the sake of future generations, they're willing to see past the hype to the benefits of clean energy. Sometimes the best solution is one already right under your nose. We need to open our minds again and rethink our global energy production and how logically, factually, that the next generation of nuclear plants is the best choice for humanity, For the planet, we need a new energy strategy. We need to educate ourselves about the issues facing the world today: the environment, poverty, the vital role of energy in our lives and very existence, and the pressing need for more energy in the years to come. Challenge the status quo with facts, not fiction. Compare the different types of energy production, and it will be evident which is the safest, most efficient, and potentially limitless source of energy out there. Today's nuclear energy and the next generation of nuclear power plants, fast breeder reactors, are incredibly safe and efficient. It's time we take notice of the new frontier of nuclear energy. The time is now.